So today we're going to be talking about the differential approach of conservation of linear momentum, more precisely the Navier-Stokes equations. Now, I would argue actually that these are some of the most important equations in all of engineering and arguably all of the field of mathematics. So I'll try to lay out some of that importance here in this discussion. Before we do that, though, I want to put up this picture, this imagery of my cup of coffee. So actually I just put in a little bit extra creamer this time, took an image of it to try to show you what the rotating structure of this fluid looks like, including basically the vortices that end up appearing now and then. Now the reason why I'm putting this up on the screen is to try to give you a sense of scale and the fact that we have similarity, as we've talked about in previous lectures, similarity between fluid mechanics structures at small scale all the way up to really, really enormous scales. And what I mean by that enormous scale is, consider this. On the right-hand side is Jupiter. It's a giant liquid and gaseous planet. What you're seeing here is what is known as the red spot. It's an enormous, basically, cyclone that's on the surface of the planet, and it has persisted for a very, very long time. In fact, it's actually been decreasing in size over the last few decades, and we've put up a really fun, interesting video of that in addition on Blackboard to talk about some of that dynamic. Now, this imagery of the red planet, or I mean not the red planet, the red spot of Jupiter, it's actually taken by Voyager 1 from NASA, and to try to give you some scale, the distance across the red spot, we're talking about over 10,000 kilometers. The Earth would actually be a little bit larger on this scale. Roughly, the diameter would be about 1.3, 1.5 across the red spot. So the next time you see a cup of coffee, think about the fact that the structures of the fluid mechanics inside your cup of coffee are consistent across the entire universe. So lesson objectives. We've got develop the differential form of the momentum equation. Second one is going to be develop the Navier-Stokes equations. Third is going to be identify the components of the Navier-Stokes equations. And then last, we're going to try to simplify the Navier-Stokes equations because, as I will present to you, they are rather complicated equations. Quick review. If you haven't already done it, please make sure that you go back and watch the video from lesson 24, where we go over the difference between integral and differential analysis, and then use differential analysis to derive conservation of mass on a differential basis. And we see that, right, that integral scale on the left-hand side, we're talking about, or integral method, the left-hand side is macro scale stuff, treating things as a black box. On the right-hand side, we're talking about micro scale, really small differential elements, and then we use that to derive conservation of mass, which is shown on the left-hand side. So that review, right, we can see integral analysis, what we used in previous lectures for conservation of mass, and now our differential analysis equation. So one thing that I should note here is that this is equation 3.13, and this is equation 17.4a to help orient you. And then the next equation that we're interested in is conservation of linear momentum. Now this was derived using Reynolds transport theorem, which gives us both the conservation of mass as well as conservation of linear momentum. And for those that might be counting at home, you could also do it for conservation of angular momentum. We just haven't covered that in MC 311 and 312. So the next step, right, is this big question mark. Big question mark is, what is the equation of interest for conservation of linear momentum on a differential analysis standpoint? Well, for those that have been listening so far, you would probably guess it's Navier-Stokes equations, right? And that's the bottom line up front. Here's a look at the Navier-Stokes equations. In a Cartesian system, so we have an x, a y, and z components. Now the truth is, this entire equation up here is x, this is y, and this is z. So we have three equations, 1, 2, 3, all the way across that compose the Cartesian direction x, y, and z for the Navier-Stokes equations. Now the thing to recognize, the most important thing that I want you to come away from this lecture with, or this discussion with, is that these really, really complicated looking equations they really just boil down to F is equal to ma, right? We go all the way back to our friend Newton, as we talked about in one of our last lectures, lesson 24. So F is equal to ma. Now, in this case, if we consider, let's say we take this rho g, right, and we look at our unit system. So we have, say, kilograms per meter cubed, and we have our gravitational constant, meters per second squared, right? So we end up with a statement that is, if we think about a force is going to be equal to ma, which is going to be equal to kilograms per meter per second squared. And as a result, we see that this is the equivalent of force divided by volume, which is exactly what we have here. Okay, so Navier-Stokes equations, they managed to flip it a little bit. On the right-hand side, it's F, or force divided by volume, and on the left-hand side, it's mass times acceleration divided by volume. And we'll walk through each of these components individually as we go. So in vector notation, the Navier-Stokes equations can be expressed this way. And it provides a shorthand notation, which is really helpful for basically simplifying this really large nonlinear. This is a nonlinear second order PDE, partial differential equation. And there are really no analytical solutions that can arrive at the answer for how you solve this. And we're going to come back to that concept here in just a bit if you don't quite believe me on that. So this is the del operator. We talked about it in lesson 24, del operator. Sig gradient, which is equivalent to del operator. So remember we talked about pressure gradient in your lab, similar to del operator, and this here is Laplacian. Essentially del or gradient squared. And that shorthand describes all three components, or all three vectors of the Navier-Stokes equation. So we'll give a quick overview of what it means for fluid to actually move through either a liquid or through gas, whatever it might be. There's four modes of transport. There's translation, there's linear deformation, there's rotation, and there's angular deformation. If you combine all four of these, you can end up actually getting the general motion of any fluid particle, whether it's gas or liquid or whatnot. So if we expand on this idea, right? So translation, basically just simple motion. This would be like, say, a coaster or something shifting across the surface of a table, but instead maybe, say, a body of fluid inside of another fluid, maybe a gas moving inside of another gaseous body. Linear deformation, this would be like expansion. Sometimes we call this volumetric dilation, stretching of a fluid particle. And then rotation and angular deformation, both are dependent upon shear stress. So you likely recall that we've talked about shear stress before in this class with our constant of, which is dynamic viscosity. And then our velocity gradient, du dy. Now that comes into play for both shear stress for rotation as well as angular deformation. By the way, if you combine all of these, you can get this complex motion of a fluid element. Now I realize this slide is very busy, but the main thing I want you to come away with on this is I want you to come away recognizing that there's translation, that there's linear deformation, there's rotation, and there's angular deformation. Is the governing modes at which fluid moves. Now, deriving this differential equation of motion, right? So we used this differential element in lesson 24. We imagined this thing being infinitesimally small, and there would also be a DZ going vertical. I just haven't shown it yet. So the intent here is to look at all of the forces that would be acting on this body. And let's imagine that we say we have pressure, and we could have pressure, right, is always normal to the surface via Pascal's law that we learned in 311. And we also have, say, at the center of this body, we'd have, what would we have? Think about it for a moment. We'd have a body force, right? We'd have a body force. I'm going to denote it as B here because we're going to be using that notation later in this discussion. But you could, of course, use a force body, whatever might make the most sense to you. Now, there are other forces that can act upon the surface of this element, and those forces might be, say, shear stress. And we would denote those as, in this case, we would say tau x, because we're on the x surface, and I'm going to write y, because I'm on the x surface and I'm pointed in the y direction. So I could draw a similar deal. So let's say we have shear stress up here. This would be tau, and this is on a z surface, and it's pointed in the x direction. So again, tau, say xy, would then be dependent upon my viscosity and my velocity gradient in the y direction, which would mean that I have shear stress as a result of viscosity, as a result of a velocity gradient that is basically trying to bend or rotate my fluid particle. Now, all of these are my forces that are acting upon this differential element, right? So this is the, remember if we talk about F is equal to ma, this is the F, right? These are all the Fs. These are all the forces that would be acting on my body. Now we also have our exchange of momentum. Now in lesson 24, we didn't have this U here, right? We only had rho u, or density times our velocity. And recall that density times velocity times dy times dz, if we look at the units there, we have kilograms, meters cubed, and then we have meters per second, and then we have meters and meters, and we end up with kilograms per second. So if we multiply by another u, now we're going to have kilograms per second times meters per second, and we end up with kilograms meters per second squared. That's equivalent to a force, or equivalent to mass times acceleration. And that's right here what we were talking about for this slide, mass times acceleration, or more accurately, basically momentum exchange across the surface of this differential element, as well as momentum potential storage inside of this element, which we're not going to dive into super deep right now in terms of the momentum storage inside of the body, but at least we're going to talk about some of the exchange across the surfaces, and then I leave it to you to look at chapter 17 of your text to derive the remainder of the differential elements. And I'll also point you to a great video that will help you understand the remainder of this derivation. So on the right-hand side, right, we have the same momentum transfer that we started with, but now we need to deal with the potential gradient as a result of moving in the x direction. So what we're looking at here is figure 17.3, and these are all the forces. So we talked about the forces just a moment ago, the body forces, the surface shear forces, etc. And we're combining them all. We're combining the body forces and all of the forces on the x, y, and z face. We're going to shift this thing over here, and we're going to call it F, right? All of our forces. And then we have figure 17.4, and we're going to shift that one to the far right. And I just cannot emphasize this enough. what we're looking at is F is equal to ma. I'm going to keep saying it over and over until you're tired of it. Okay, so it's F is equal to ma is all the complexity that we're dealing with here. And that gets us to the first form of the differential form of the momentum equation. Okay, so this is in the x direction. We have the x direction of the differential form of the momentum equation. So this is the x direction. And now, for the sake of confusion, the standard convention when writing out the differential form of momentum equation and the Navier-Stokes equations is to actually flip it. So mass and acceleration are on the left-hand side, and force is now actually on the right-hand side. So really it's now mass times acceleration divided by velocity is equal to the force in that direction divided by velocity. Or, I mean, divided by volume. Sorry, when I say V there, these V's are volume. My apologies, I just misstated that. Okay, so this term, we describe this as local acceleration. This represents the amount of mass that is being, mass and momentum, more accurately, momentum that is being either stored or basically extracted from our control volume. This is what we call convective acceleration. And it represents the mass and momentum that is being conveyed across the surface of our differential element. And then we have all of these terms over here are net shear. Now that net shear is both normal as well as basically tangential to the surface. Now normal shear stress often is denoted by pressure, right? So these are pressure terms. And then we have our body forces due to gravity. Body force due to gravity. Now, there could be other body forces like magnetism and such, but we're not dealing with that right now. Wrapping back to this idea of net shear, it is possible to have a normal shear force as a result of, say, viscosity, because of the cohesive bonding between, say, water and itself can actually result in a normal shear stress that is slightly different, or a different description than what we normally describe as, say, pressure, which is the thing we're normally dealing with for normal forces. Okay, so when we think about this whole thing, we now have three components, or three directions rather, x, y, and z, of our differential form of the momentum equation, where B in this case now, as I said earlier, is our body force. And this is our vector notation. This is our vector notation. And the vector notation is the same thing as our x direction, y direction, and z direction. It's the same expression, just shorthand. One of the biggest things I want you to take away from this slide itself is that we've actually made no assumptions. We've made no assumptions up until this point, which means that this equation, we've made no assumptions, no major assumptions, and this equation is valid for fluids and solids. Okay? It's also valid for statics and dynamics. It's a really powerful description of basically conservation of momentum across almost any body that you're interested in. So the question now is, how do we take this and apply it to the realm of fluids that we're particularly interested in, with things that say like have viscosity and really want to move as a result of shear? And that gets arguably even more complicated, which is what we're going to start diving into here in just a moment. So that checks off numero uno, right? That checks off our differential form of the momentum equation. So now the question is, or now the next step is, we need to try to develop the Navier-Stokes equations. So I do want to make a couple quick comments about the Navier-Stokes equations. This is the Clay Mathematics Institute, or CMI. They are a leader in the field of mathematics and trying to basically, as their title describes, disseminate mathematical knowledge. Now, they set up what is called the millennial problems, or millennium problems. And these were determined to be some of the hardest, most important problems in all of mathematics. And this says, right, the prizes, the Millennium Prizes were conceived to record some of the most difficult problems with which mathematics were grappling at the turn of the second millennium. They have put $1 million prize on each of these 7 problems that they identified. If somebody can provide a solution, essentially, it's basically like an X Prize, right? To try to push the frontier of mathematics and to try to take us to a place that we have previously not been able to get to when it comes to mathematical methods. One of those problems is developing an analytical solution to show smoothness of the Navier-Stokes equations, because there are discontinuities in it. There's so much complexity in this nonlinear second-order partial differential equation. It's immensely challenging. Now, it's also immensely important because the amount of fluids, basically, that we interact with on a daily basis in our basically professional and private lives, in the development of medicine, in the development of better working systems, engines, whatever it might be. It's an incredibly important field. Here is one of the individuals, one of the namesakes, George Stokes. The next individual, who I don't want to leave out, right? So here's Claude Navier, the French engineer. Stokes was an Englishman. They both have basically been credited with development of this differential analysis and the assumptions needed in order to derive the Navier-Stokes equations. So I hope it's needless to say at this point, Navier-Stokes equations are both incredibly important and incredibly complicated. So some of our effort is to try to understand how we can simplify them and then use them in daily analysis. Now, one of the ways that we can do that is through computational fluid dynamics, and I mentioned this in lesson 24, but I do want to show you a couple more examples. This is one of those examples. This is a graphic from Deep Impact that came out in 1998. And one of the ways we solve the Navier-Stokes equations is actually by throwing an enormous amount of computational power at it in order to basically get around some of the complexity that we can't solve analytically. And so the directors of that movie actually came up with a scene that they wanted to see this giant tsunami after the asteroid strike impact basically run all this water through basically downtown Manhattan. And at the time, they didn't have great computational solutions and hadn't really developed it well. Now, granted, it was quite interesting because one of the individuals who helped develop this graphic that you're currently seeing essentially independently came up with the idea of having these small, what are called voxels, or these little tiny differential elements through which fluid would flow. And if each of the voxels filled up with too much fluid, well, then it spilled into the next little grid that was used in this simulation. Now, it wasn't great at the beginning. They didn't have great resolution. Their computational power wasn't that great. In 2004, actually, the very similar team working with the same improved code actually then put out this graphic for the day after tomorrow, where once again we have an enormous amount of water flooding through Manhattan. And now I don't know why we're constantly wanting to do that, but so be it. But the interesting aspect here, right, is the improvement in the resolution of these systems, and this is all often using methods that would fall back to the same idea of Navier-Stokes equations and conservation of mass, conservation of momentum as these fluids flow through a certain matrix. So the movie industry uses Navier-Stokes equations. In fact, they acknowledge it in these description of some of the software programs that they have here, right? So Maya simulates fluid motion by solving the Navier-Stokes fluid dynamics equations at each step. So they throw enormous computational power at these problems in order to try to basically model what fluids look like in the absence of an analytical solution to actually solve the Navier-Stokes equations. And that work ends up manifesting itself in all of these types of graphics that you can see here. So these viscous fluids on the left, these molten lava, we have explosions, we have the surface of the ocean, we're flying through clouds. All of this represents sort of manifestations of the Navier-Stokes equations. And that same team that actually was involved with some of that early stuff on deep impact, as well as the day after tomorrow, that work on that water that was flowing through Manhattan, was actually also involved or supported some of the work that eventually Disney put out with Moana and Pixar. This kind of revolutionized water in the movie industry, at least in terms of computer graphics, and created extremely realistic fluid. And again, it's based off Navier-Stokes behavior, conservation of mass, conservation of momentum. So in addition to the movie industry, of course, fluids is extremely important in a variety of other fields, including defense, as you might imagine. Right. So this was footage of an artillery shell coming from a D-20 or 152 millimeter former Soviet Union artillery piece. Really, truly incredible footage, frankly. And we can see the behavior of the muzzle brake. We can see the expansion of hot gases. We can see lift and drag of the projectile. We can see impact on the target. All of this is related to fluids. Los Alamos National Labs has also done simulations using Navier-Stokes equations and simulations to model what it looks like for large asteroid impacts. We're talking like 100-kilometer type scale, like the type of thing that basically wiped out the dinosaurs. So on the right-hand side, what you're seeing here, the scale of these impacts, it's almost hard to imagine. This is, as it says down here, about 100 kilometers high. 100 kilometers. Try to wrap your mind around that. In terms of, this is basically molten rock that has been basically turned into a fluid as a result of the asteroid strike on the Yucatan Peninsula, and then distributing all of that across all of Mexico and the Gulf of Mexico, and then subsequently basically tsunami rolling into North America. Really pretty remarkable stuff. Again, this is going back to basically what we can do with large computational power being thrown at these problems. So circling all the way back now, after some of those examples, let's talk about developing the Navier-Stokes equations. We started with a description of conservation of linear momentum using a differential form of the equations of motion, which is just F is equal to ma, right? But now we're talking about differential form of that. So we have three assumptions that we're particularly interested in. We have incompressible fluid, we have an isothermal fluid, and we have a Newtonian fluid. What does the last thing mean? Right, so let's do a quick reminder. Newtonian fluid, this is from chapter 1, means that we have this description, which we actually wrote down in this exact class or exact discussion just a little while ago. It basically means that the fluid deforms linearly as a result of a shear stress. That's all it means. It means this is linear. Now, there are other fluids that behave differently. There are things like called Bingham plastics that have to have a certain amount of shear before, or pressure basically, a certain amount of stress before they end up actually moving. That would be like toothpaste. Toothpaste is a Bingham plastic, whereas Newtonian fluid would be things like water, oil, gasoline, and air. Okay? So if we have a linear deformation as a result of a shear stress, we have a Newtonian fluid. Now, if we go back to that equation of motion that we talked about earlier, this is, let's say, equation 1. This is our differential form of the equations of motion. We then have our conservation of mass equation, or what we call continuity. And then last, this table 17.1 These assumptions here are both shear stress that you've seen, but it also throws in a little bit of mix of some basically hypotheses from Stokes, and the appendices in your text can also help you walk through this. So then let's say this is equation 3, even though it's a variety of equations. If we take these equations, basically 2 and 3, and we put them into 1, and we throw in a dash of those assumptions that we just had there, we end up with the Navier-Stokes equations. Again, I will point you to chapter 17 of your text for additional discussion on that, and I'm also in just a moment here going to point you to another great video that you can watch to walk through the full derivation. So we end up with these 3 components, or these 4 statements, are x, y, and z Cartesian coordinates, x, y, and z, describing our Navier-Stokes equations. Now, on the right-hand side, these are in blue. All of these terms are in blue because this is very specific to being an isothermal Newtonian fluid, right? So isothermal because U is a function of temperature. And when I just said U, I really meant to say mu, which is our dynamic viscosity, is a function of temperature, and as a result of that, we need to say that this whole thing is isothermal. The whole fluid that we're dealing with is isothermal, so that we can bring this mu out. If it were not isothermal, then this mu would need to be distributed in each of these locations, and in fact inside of the derivative, which would make things very complicated. Now, it's also incompressible, and that's really helpful because we were able to pull the rho, or the density, outside of the differential analysis on the left-hand side. Now, as a reminder, right, as I've reminded a number of times now, this whole thing is equal to, F is equal to ma, or in this case, mass times acceleration divided by volume is equal to sum of our forces divided by volume. We could also express this in our shorthand notation or vector notation, again using basically our del operator and our Laplacian. This is our del operator, or gradient, pressure gradient. So that's number 2. So we've checked those off, okay? So now we need to get to number 3, which is identify the components of Navier-Stokes equations. We'll knock this one out quickly. So let's take the x direction. X direction of the Navier-Stokes equations. Again, m is equal to, or ma is equal to f on the right-hand side. The term on the far left is our local acceleration, or the rate of change of momentum within the control volume. The next few terms are our convective acceleration. It's the net rate of momentum flow exiting or entering basically across the control surface into and out of the control volume. Next one is our body forces, weight. There are other body forces, but we're only focused on basic gravitational or body forces as a result of gravity, and then our net pressure force in the x direction. And then the far right hand being our net viscous forces. Again, going back to that idea that we talked about at the beginning, that we're primarily dealing with, say, tau xy is equal to mu du dy, is one of the primary drivers here that shows up or manifests itself on the far right-hand side. So that's number 3. So now we've checked most of them off. Okay, so we've got a couple more things to cover, and then we'll wrap this up. This is the video that I strongly recommend you go watch to take a deeper dive into the derivation of the Navier-Stokes equations from Professor Jeremy Knudsen at the University of Colorado Boulder. It's a good, succinct explanation, and that is provided on Blackboard for you. So this is one of the examples that I want to look at, something called Poisson flow. So as we've already talked about, Navier-Stokes equations are quite complicated, but there are a few unique cases that we can simplify flow down to a point where it is actually, we can solve it analytically, which is really nice, very helpful. So the question at hand is for you to take the Navier-Stokes equations, all three directions, x, y, and z, and simplify them for this case. And we're going to do that with a variety of assumptions. 7 assumptions, that is. So we're going to say, number 1, our first assumption is that this thing is two-dimensional. So if it's two-dimensional, let's say it's only in the x and the y direction. As a result, we could say that the partial derivative with respect to z is going to be 0, right? And then let's say it's fully developed. And so when I say fully developed, let me be more specific. And we'll say that this is the x direction. This is the y direction. And this is our height between the surface, or the two surfaces. We have an entrance length, which we've talked about in this course content leading up to now. And then we have a fully developed region, where it's fully developed. And this over here is the region that we're really interested in. Fully developed region, not the entrance length. So we're saying it's fully developed, so everything over on the far right-hand side, if it's not changing with any increase in x, then we could say that partial derivative of x is equal to 0. However, except we'd say that the pressure gradient might not be 0. And what I mean by that is that we still have pressure loss as a result as we change in the x direction. But we don't have, say, any change in the velocity. So steady state, we said it was steady state up here. So that means we have no change in time. So d dt is equal to 0. Newtonian, that's going to come in to be helpful because of where we can place our dynamic viscosity. And then we have laminar, or that it is laminar, and we have flow is purely in the x direction. That means our velocity component in the y direction, small v, is equal to 0. It also means that our velocity component in the z direction is equal to 0. And that is true everywhere. Okay, and then incompressible, our density is constant. And then last, gravity's in the z direction. That means gx is equal to gy is equal to 0. Okay, so let's work to try to simplify these things. Here's the equations of interest that we're really looking at. We said this is a fully developed flow, right? So from the assumptions that we had on the previous page, we could say du dx is going to be 0 because of assumption 2. We could then also say dv dy and dw dz. These are also 0, but in this case, it's because of assumption 5, right? We said there's no velocity in the y and the z direction, and as a result, there is going to be no change in the y and the z direction if there is no velocity. So then we're dealing with our x, y, and z directions of the Navier-Stokes equations. So we have our x direction, y direction, and our z direction. So we said it was steady state. Everything with respect to time is going to get canceled out, and that's from assumption 3. We said it was fully developed. So that is number 2. We said there is no velocity in the y direction or in the z direction. So this can be canceled from 5. Now, this term, truth is, some of these terms could actually both be canceled out as 0, but of course we only need one 0 to really cancel them out. And then gx, we said this is 0 because of the direction of how we defined where gravity is pointing. That's number 7. Our dp dx, our pressure gradient in the x direction, is non-zero, actually, so that's decreasing, so we can't cross that out. We did say this is fully developed. That's number 2. That's getting canceled out. We do have a change in the u velocity with respect to y. Let's revisit that idea. So we have that pipe, right? And we have a flow inside of this pipe. And so if we move up in the y direction, our velocity u increases. So this is u of y, which basically means that this term here is non-zero. So we can't cancel that thing out. So that's got to stay. However, in the z direction, this can get canceled out. So we said that it's two-dimensional. So this is number 1. Numero uno assumption. We can cancel that one out. On the next, in the y direction. So actually, let me come back here real fast. So now in the x direction, we have a term that says 0 is equal to our pressure gradient plus our shear stress component of du dy, second partial of it. So now on the y component, we can cancel dv dx because of 5, dv dy, similar statements. We don't have velocity in the v direction or the y direction. Same here, number 5, it's being very useful, cancel out a lot. And then 7, and then we have in the x direction, we don't have a velocity or we don't have a change in the y velocity as with respect to x, is what this statement meant here. We have the same deal here, 5, and then last, same. We can cancel those all out. Now we are left with a statement that says that the pressure gradient in the y direction is equal to 0, which essentially means that the pressure is constant in the y direction, which by inspection you likely could have figured out, but it's nice to see that Navier-Stokes equations are going to be consistent with that. On the z direction, dw, we know that that is 0, so we can cancel this out. We could either use actually the first assumption or number 5. We can use 5 across the board here, and then we are left with the last few terms. dw, there is no velocity in the z direction, so these all get canceled out. And then we're left with a statement that is 0 rho gz minus our pressure gradient in the z direction. Now, if you took this statement here and you integrated it, what you would find is that the pressure with respect to z is equal to the density times gravitational constant times some height h. Well, that is pressure is equal to rho gh. That is hydrostatic pressure. That's precisely consistent with what you learned in MC 311. So the Navier-Stokes equations, when simplified, are going to give you a whole lot of equations that you are already familiar with and they should match your intuition. So despite the complexity that they have here, if you simplify them properly, you're likely going to end up with equations that appear relatively familiar. So in this case, it means the pressure in the y direction is just some constant. So the last real question mark, right, is now in the x direction. So I'm going to leave it to you to figure this out. But what you have now is you have a statement that is our pressure gradient divided by our dynamic viscosity is equal to the second partial of u with respect to y. And if you work to integrate that, you should come up with a function that describes our x velocity as a function of y. Now you will need to pay attention to what are your boundary conditions. Okay? Give that a shot. If you have trouble with that integral, there is a solution that is available on Blackboard. Please review it. All right, so that wraps it. That covers all 4 of the lesson objectives. A couple final comments. Your homework number 4 is due on April 3rd, coming up here pretty soon. I would also strongly suggest that you check out the videos that we provided online. There's one additional footage of Moana. I would check out, go see the all the varieties of water in that movie. Really quite remarkable. There's also another video on Jupiter's red spot, give you additional perspective on how large that system is. And then whenever you're seeing fluids flow around, whether it's in a diner or out in a river or wherever it might be, you realize that Navier-Stokes and all these physics, they're all the same everywhere in this universe. So hope you've enjoyed it, and I hope you have a great day.